So welcome back. Hopefully you've had a little bit of time to look at the template that I provided. And just now, Ali just copied and pasted in the first cell that had code in it with an updated piece of code. You'll notice that it's very, very simple in that there's only linear layers here. There's no convolutional layers. There's no specialized layers at all. We did that for a reason, to keep it simple so that you can build on top of this if you want to. I just had a question saying, do you need to specify xdim, which is the dimension of the input? No, you do not. If you would like this to be more interchangeable and a better model for shifting to different tasks, what I would do personally is wrap this around a sequential model. And a sequential model, you can feed pretty much anything into there and it'll just adapt according to your input size. And you could put convolution layers into there, adapt the filter size, the kernel size, and it'll just take whatever's fed in and just do the operation regardless of the input size. So that way you don't have to specify exactly what the input dimension is. So wrap all of your FC layers, I guess, here, all around a sequential model. And when you call the sequential model, so when you call the forward function and you call it for training, you just give it an X, which you will get from your data loaders, and it should just adjust automatically. It shouldn't need to know what your dimensions are. For the linear layer, yes, they do, but for convolutional layers, for example, if you just kept the kernel size as 1 or something, then no, you wouldn't need to.
Because I also saw some tutorial online. They always use the function view for for example 2D dimensions or the LSTM
yeah. No, you don't have to flatten it out. You don't need to do view and then -1. You can keep them in the original dimensions. So have batch size times the width times the height times the number of channels. So that's your 4 dimensions there. And you can pass it in like that. So your batch would actually be that shape. And then that could get fed into a model.
Batch is always the first dimension.
Yes.
Okay.
Yes.
So do you mean it will be flattened out automatically?
No. So this implementation here, because I use linear layers and there's no convolutional layers, they're all flattened out for that purpose. But if you want to use convolutional layers, which I would highly recommend since you're using MNIST and you want to take advantage of that translation and scale, I would change those to convolutional layers actually, and so have that 4-dimensional input, and it should be able to adjust accordingly. And that way you don't need to specify xdim. You still need to specify hdim, zdim, because h is your hidden layers. You need to tell it how deep you want it, how your width, how wide you want your network as well in each layer. And you do need to tell it zdim, because that's the number of latent embeddings you have in that latent space. So the number of units or the number of variances, that's zdim there. So specify that, because that's basically how complex you want that embedding to be. So definitely put that into there. But the xdim, you can replace that and get rid of that altogether if you decide to use convolutions at least. You have a sampling function there, which tells you how typically we sample from that Gaussian distribution. And in the forward function, you'll see what I was talking about earlier. We call our encoder, pass our X into there, get rid of this. If you don't want to flatten your image, it would just go in as X. And from X, from the encoder, you're returning the mean and the variance, which I specified up here, the mean and the variance. And then they come back from the encoder. We call our sampling function, which takes our mean and variances from the unit Gaussians and gives us Z. Then Z gets fed into our decoder, which then gives us a reconstructed X. I apologize for these naming conventions. This should really be something like mean. This should be something like log var. To make it more readable to you guys, but you get the idea.
So one clarification, there was a question about Z dimension, which is, we thought it would be the dimension of the output, but now I looked at the code, this is the dimension of the encoder, which is there are 2
Yes.
versus, and like in the last layer of the decoder, we have xdim, which is exactly the same as the
exactly the same
dimension.
as your input dimension.
Yeah.
And if you decide to get rid of xdim altogether, that should be the same size. If you flipped it correctly and you've not added anything weird in between, the output should be the same size as the input. Without having to specify xdim, you should be able to do that. Zdim is indeed the size of your embedding, and you have two here, two linear functions here which have zdim associated with it. And they both have the same input as well, note that there, HDIM2.
So again, you have the output of the encoder coinciding with the input dimension-wise, the input of decoder. This is not a general case.
The output, sorry, can you
So you have zdim variances and zdim means.
Yes.
And then you have zdim samples. No?
Yes, you have zdim samples, correct.
So the number of variances should correspond to the number of means, obviously.
Yes.
But the samples could be just a different number. You can just write zdim plus one sample or plus any number.
I guess theoretically you could, but I think it's normally the same because you kind of want to keep. You don't want to drastically change that latent space dimension, because then your decoder is going to have to do a lot of extra work to figure out what's happening, I would imagine.
But it's not the latency. So you have.
So you kind of want one sample per Gaussian there. That makes sense intuitively, right?
Why? No, it doesn't.
Like one sample per unit Gaussian?
Yeah. You can't estimate a variance from one sample.
I mean, if you need more from your latent space, I would rather expand Zdim to be bigger so that you have a bigger sampling. Because then the complexity is kind of similar between the output of the encoder and the input to the decoder. That's how I would do it personally, but theoretically, there's nothing stopping you from doing that.
I wonder if there is a reason for the numbers. Okay, we want to keep the architecture symmetric, so we don't want the numbers to be drastically different.
Yeah.
But there is.
Like, what benefit would you get by going off symmetry?
Just makes it a bit harder, right?
It just
Again,
makes
variance.
it a bit harder.
Variance. I don't know the variance, because if the number of I have one Gaussian distribution. I have batch size 1 goes through. I draw one sample. One sample tells me nothing about variance. It tells me something about mean.
Yeah.
When I repeat, if I have a batch going through, again, each example in the batch tells me nothing about variance. So my incoming layer of the decoder cannot learn.
So it's not telling you anything, because now your mixture of Gaussians, which we talked about earlier, is now just a Gaussian. You've actually changed your function, the purpose of your function now, so that now it's just a Gaussian. So I don't know any situation where you would have a one-dimensional latent space. Really, you want a mixture because you want to capture.
What do you mean by latent space?
Are you saying zdim equals 1, or are you saying your batch size, you're feeding it one sample at a time?
So
you're saying both, aren't you?
Are you saying both? Or is it saying
yes. Batch size is just an example to illustrate.
Are you okay if the zdim is 20?
I'm okay with zdim being 20, but then I have 20
variances to fit. Yeah.
So what I'm afraid will happen is that the variances, they will just the Gaussian distributions, they will just group together and will be identical on the output of the encoder, so that the input of the decoder could learn variances from them.
So the way the loss function works, unless you use beta V and bump that weight value right up, then that possibility can occur where all of your Gaussians would just go towards 0. But because of the way the loss function works, it balances both. So it does kind of, I think I had it in the lecture, one particular slide where I showed you 3 Gaussians around the unit 0. So because the way loss function works, it does try to separate them out, but just not too much like it does with an autoencoder. So unless, you bumped up that second regularizer term, there's no way that it should all go towards 0 too much in that they overlap. They shouldn't really overlap to that level.
So why would they naturally prefer to be separate? What keeps them apart?
So the reconstruction part of the log likelihood of the loss function should keep them apart. Because autoencoder does that, it keeps them way apart because it relies on just log likelihood.
Yes, but if I have very many parameters, very many these Gaussian distributions, like an overfitting scenario, then some of them
you're
will
right.
be
It could overfit if you went far too big for your data. Yeah, you can absolutely. It's a good point. Back to our original point. Still interesting. So you're saying why does ZDIM and FC4 here have to be ZDIM? Why can't it be something else? That's your point.
You know, I think it's a good idea for the capstone. You can have different implementation and see like how do they perform, and that will be a really good that will be a good blog post and a Git repo, because I don't know if someone already did it, right?
No, I don't.
So it's a good idea actually, like if you want to do it.
Yeah, what I'm afraid of it is someone showed that making things more complex does not give any gain.
My hunch is that's probably the truth.
Yeah.
But
it's learning.
It's learning, yeah, exactly. And I think it's a great idea to use Capstone project to look into things like that. To look into non-Gaussian distributions, that's another great Capstone project. We were actually talking about it during the practical session for those guys who are online. And the guys who are very, they know their stats really well, don't see any reason why you couldn't use non-Gaussian distributions and adapt the rest of your model accordingly. And I think that would be another great project to try out as well, with different types of data. So we were talking about MR data that comes in case-based form, so Fourier transform form. So lots of ideas to try out there. So yeah, to round off, there is a little bit of code for you to play with. Have a look at it, try to digest it. I would highly recommend changing those linears to columns, and maybe wrapping that around a sequential model, or even just keeping it there, but changing them to convolutional layers so that you don't need to worry about XDIM. And we'll release the rest of the cells as we go forward. Good luck, everyone. Okay, guys, it's getting. Oh, you have a question? Go for it.
More so for next week. If we brought our own data, can you help us build a data loader?
I can certainly do that. Yeah, I'm sure we can do that between the two of us. Yeah.
Yeah.
Thank you so much.
Absolutely. I've built one before, so yeah, theoretically we should be able to get it done.
Thank you.
All right, guys, so this is just an update. Hopefully you've had enough time to play around today, and I don't want to leave you guys too late. So what we've done is we've just released all of the code for this week online on the Colab notebook. I forgot to say, you need to re-grab the Colab notebook if you want to update your code and update your models. So you'll notice that the loss function has also been included here as well. We just found out that there's a KL diversions built-in loss function, which is good to know, but we've actually just implemented it here because it's fairly simple to implement as well. And you'll notice that it's made up of two terms. One is cross entropy. So here we use the built-in torch function, cross entropy, but you could have very easily done that yourself as well. You didn't have to use a built-in loss function. And here's the KL divergence, and simply it's an addition of both. It's nothing too complex there. And the train and test functions are virtually identical to the ones on the tutorial that I mentioned, the 60-minute blitz one. I barely touched it, so it should look very, very similar to that. One thing I did leave out before was this model.toDevice. So in order to move your device, your models to your GPUs, for example, then you need to change this. You need to include this as well. And that's it. This is fully functioning. It should run. We've all been using it. Me and the TAs have been using it to sanity check and to try out different things. Feel free to modify it, use it. We're actually going to build on top of this next week because we'll be building the variational deep embedding network, which is a clustering network. And it takes VAID and just kind of extends it out a little bit more. We'll be adapting that loss function. So keep this on hand. If you want to edit it without breaking it, just create a copy. But you'll have it available on Google Drive regardless. And with that, thank you very much, everyone. And we'll see you next week. Yay. Do you have anything addition to add?
No.
No?
I have a question. So in the past, I've used KL divergence. It's calculated empirically, like it's calculated as a for loop over the probability bins.
You've never seen it like that?
This is like an identity.
No, it's not even using the GPU.
I mean, isn't it still, because the loss function returns, I'm wondering if this is still like a vector that's returned and then it gets mean and average later. Just gonna look at this very quickly. Loss function. No, it doesn't seem to be mean. Let's just have a look at this. Wrong one.
Actually,
Fairly sure this is the one on collab.
do you have the exact same color?
Okay. Let's have a look at this. Yeah, I think it's just one value that's coming out of here.
I can just go back to the original one. Yeah, make a new copy. Right. Yeah, that's fine. It might be something.
Yeah, there's just one value.
Oh, are you running a different page?
Yes.
I'm not getting the screen share.
Oh, yeah, this is on Safari.
Oh,
This is your screen share? Yeah?
yeah, can you move it to Chrome?
So that's Chrome?
No,
Or change your
so I'm getting that.
Yeah.
But,
Well, because I was just, this is off. Yeah.
Oh, so you want to cut the live stream?
I think so. Do we need to stay online for longer?
I thought we can also address
There
the
are more
questions.
question and answers.
Yeah.
Okay. Okay. Because the thing is, even if you use the built-in KL divergence term, it would do the same thing. It would do them independently and then just add them together.
Yeah, I'll look at the paper and the.
Yeah, I'm gonna have a look at the PyTorch documentation as well.
I mean, from the code, I think they do it in the definition, right? Because they didn't do it empirically. Because we know the mean and the standard deviations, so we can calculate the KL divergence between the standard Gaussian and all the distributions we have in the latent space. Yeah. So we didn't do it empirically because we don't have the data, like we don't have all the samples from the distributions.
Right, yeah.
So we did by the definitions of the
Got it.
divergence. Yeah.
Yeah,
Which creates a new.
yeah, that makes sense.
Then
Yeah, you're right, we don't have all the data
check
on
your
hand. So we've done the modeling part indirectly, and
use an
then,
identity.
yeah, we're making major assumptions with this KL divergence function, yeah.
When I ran the copy of the notebook that I downloaded from you, I got a type error.
Oh
Yeah.
dear.
something like that. Let me double check.
What's the type error?
So I guess in the solution we have an error when I copy paste it, so I'll find it and send it.
Oh, I see. Okay.
So I'll find it. I don't know where it is exactly.
I'll just post this.
Yeah, just
So the reason we use binary cross interface is because the pixel is either black and white, so it's either 0 and 1. So if there's like color picture, it should be cross, like just normal cross interface.
Yeah.
Okay.
Exactly. Yeah.